Hey, this is Patrick Sackett with Covert Channels, Dr. Watkins, Johns Hopkins Assignment 2. For this assignment, I decided to implement a rudimentary HTTP-based covert channel. This covert channel, from a very high level, operates essentially like a Caesar cipher. So the basis of this covert channel is a mapping, really utilizing status codes that are common with HTTP, of which we can see we have listed here. For each status code we have, we map that to a letter, and we also map a status code to just a blank space in case the data we want to exfil includes blank spaces as well. So essentially, starting this program, there are three pieces to it. The sending functionality, which all is needed is a IP address and port number for the target server. There's a receiving functionality, which just specifies the interface and port number to listen on for the client to reach out to. And then there's a mitigation functionality, which we will touch on in a bit. This really just works by overriding the base HTTP request handler class with an implementation of our own. Here we override their base implementation of the do post function. So with this function override, every time that our server receives a post request, it will execute our code instead of the standard code for that library. So starting off with the program, the user is going to specify a number, an integer, for the amount that they would like to shift the cipher. So instead of just plainly mapping each status code to each letter, we ask for a shift index, of which will help prevent any outsiders looking in to be able to easily determine what our cipher is and how we're mapping each status code to each letter. So each time the user can choose a different shift index, although they do need to be the same for both the server and client in order for the message to be successfully encoded and decoded. And then on the server side of things, the user will be prompted to input the secret data that they would like to exfil. So for this covert channel, it's assumed that our receiving functionality, for the server functionality anyway, we're running presumably on a target, and there's secret data we want to exfil back to our C2 server, which would be the client. So initially, the client will reach out to the server with the initial post request, of which the server will recognize as the first message or request being sent. So it will send back the length of the message, with which the client will then generate a post request for each character within the secret data, which the server will shift its index and send back the appropriate character or error code. From the outside looking in, it will seem as though there's just a random rogue client trying to communicate to a network device within the network, and is receiving random error codes and random 200 OK status requests. But in actuality, we'll be exfilling secret data off the target back to our C2 server. One thing we do as well, we do randomly generate data to tag onto our post requests, so they're not just empty post requests. This is just an attempt to try to blend traffic a little more. And that's really just a broad overview of what we have currently implemented. So if we move over to some of our virtual machines that we have running, here on the right we'll have the receiving functionality implemented. So this will be our server running on the presumed target machine. Then on the left we will have the sending functionality. This will be running on presumably like a C2 server, and this will be reaching out to our receiver. And then our third VM will be showing the mitigation technique for this covert channel. So of course there would be methods that you could take in terms of packet analysis in order to easily identify malicious traffic. Here would just be a abundance and really weird blending of different status codes that would probably trigger a network-based intrusion detection system to detect this covert channel. But for this specific mitigation technique, all we've really implemented is a flood attack. So the current implementation for this code does not take into account tracking different clients with different indexes, so really anyone could theoretically connect to our server running on the target and start sending post requests, which will then throw off the server tracking where the actual client is with its own index and start sending invalid data. So we'll see that in live action here in a second as well. So let's go ahead and boot up our receiving server. As previously mentioned, it really just takes a version of Python here, version of Python 3.10. We're going to specify receive, and then we're going to specify the interface we're listening on along with the port number. Once we hit enter, we're going to be asked for a shift index. Here, for example, we could just use 7, and then the secret message to send to the client. So here we'll just do test. We're now listening in port 8080 for the client to initially reach out. On the left here, we will be running the program with the send flag along with the IP address of the server and the port number we want to connect on. Once we hit enter, we'll be asked for a shift index. So again, these shift indexes should match, otherwise the cipher will be thrown off on one side and the secret message will not be deciphered correctly. So we go ahead and specify 7. So a few things just happened there. One, the server did receive the first post request. It sent back the length of the message, which here is 4, and our client then sent 4 post requests to the server with which it sent the appropriate status code. So first, for the length of the message, we just send a 200 and we append the length of the secret message, which I'll run again and show in Wireshark here. Then we send 1 status code per letter of the secret message. So now that our server knows that we sent the entire message, it will reset the index, and so we can send another request for that message. So let's go ahead and open up Wireshark as well here, just so we can see the packets in action. For shift, we're going to specify a shift index again. Here should be 7. Go ahead and stop our capture. We see here with our .130 IP address, we send our first post request to our server, then the .133, our server responds first with the message length. This is HTTP OK, and here we just have a header field with the integer of the length of the secret message. From here we just see repeats, so this .130, our client will reach out with a post request with randomly generated data, which we can see appended to the packet, and then we'll have the appropriate status code here, 510 representing T, sent back to the client to decipher. Again, post, we'll have 403, we'll have post 502, and we'll have post 510. So here let's also go ahead and show what happens when we run and our cipher integers are off. So instead of 7, we'll specify 8, and we see we do not successfully print test because the 2 shift indexes are both off. So let's go ahead and show also our mitigation technique. So as previously mentioned, with the mitigation technique, we're just going to use the mitigate flag. We're going to use the IP address of the server and the port number we want to connect on. So this would be a third party that intends to disrupt our covert channel and prevent our client on our C2 server from receiving the secret data being exfilled off target. So our server's still running. We're going to go ahead and launch our mitigation technique, which will just start flooding the server with post requests, which will then throw off the correct shift index for the server as well. This means as soon as we send the request to the server, that the message it sends back will be off. And we go ahead and specify a shift index of 7. We can see on the right we start returning packets. Then on the left, once we try to connect with our client, specify the shift index of 7, and we see the message is incorrect. Here we get ETTS. Depending on when we connect to the server will depend on what type of data we get back. Here, because we don't even receive the proper length of the secret message, we can see we get a parsing error in the client. So go ahead and stop our server, and that's it for the brief overview for assignment 2. Thank you.